I think there's one other challenge here as well in terms of designing for high-speed channels like a group of CSI lanes, which is the interconnect from the webcam or some other peripherals back to the motherboard. And inside of a laptop, of course, it's mounted up on the top of the screen, so you can't just throw a cable on there and then run the cable back down to the bottom of the laptop body and then plug that in. You have to design something like a flex ribbon. So is that the approach you took?
Yeah, that's a very good point. Designing this flex cable is also an interesting challenge. But that's actually also one reason why I would like to move this topology towards a USB UVC interface, because routing one USB-C pair through the whole laptop lid is much easier than routing the whole CSI interface through the laptop lid. Because now, if you do this, we have to deal with quite a bit more challenging signal integrity situation, I would say, because this flex cable, for one, has to be sandwiched between the aluminium tray of the lid itself, but also the display panel, which also has a metal backing. So we have a PCB that's sandwiched between two metal parts, meaning we can't use a two-layer board, because if we use a two-layer board and don't define exactly how this cable sits between those two metal parts, we will have impedance discontinuities depending on how the ribbon cable is integrated into this sandwich, I'll just call it. And the other thing is the ribbon cable itself, or the flex cable, still needs to be very flexible, because it has to go over the hinge mechanism in the laptop lid. Meaning we have to make sure we're still within our target impedance, but we also have to make sure the flex cable is still flexible and won't break after a few cycles. And doing this requires using as little copper as possible in the flex region, but also making sure that we are still hitting our target impedance. Means we have to use a hedged reference plane, but that now comes with the challenge of calculating the impedance over a hedged reference plane for those differential pairs. And there is no easy way how you could approach that analytically. So there is not a simple equation that you can just use that spits out the target impedance based on the fill factor, for example. We actually have to go through the whole simulation process. You have to mesh this very intricate and complex hedged reference plane with all the differential pairs above it, and try to work out the target impedance in an iterative way, in an iterative manner in this way. And we've talked a bit about that behind the scenes as well. And just the simulation setup gets very, very involved. The mesh gets very large and stuff like that. So that was also quite a fun challenge to work that out.
Yeah, it seems like it should be really simple, right? It's just a copper grid. But when you actually go to set up a 3D simulation, all of a sudden it's taking forever, whereas the exact same board, but with a solid plane, actually goes extremely quickly.
Yeah, exactly. And it gets even more annoying once you have bends over this hedged reference plane, because if everything is aligned and in parallel or perpendicular to another, the meshing is much easier. But now if you have those curved traces above a hedged reference plane, the meshing gets really involved, and you basically have to run a FEM simulation on that. You can't use axis aligned grids and stuff like that. You really have to use a very fine tetrahedral mesh, for example, and that just gets very, very large depending on how large your simulation domain is.